The concrete is 2 feet thick, reinforced, poured in sections between 1921 and 1925. Along the entire 5.022-mile length of the Connaught Tunnel beneath Rogers Pass in British Columbia. The engineers lined a tunnel bored through predominantly stable granite bedrock. The rock wasn't collapsing. Water infiltration was a possibility. Not a certainty. They poured the concrete anyway. The liner has lasted 99 years without major reconstruction. The tunnel remains operational today, carrying transcontinental freight through the Selkirk Mountains. The original concrete endures. The context reveals the decision. Rogers Pass, at elevation 4,364 feet, presented Canadian Pacific Railway with an unsolvable problem in 1885. The surveyed route over the pass required steep grades, 2.2% in sections, and exposed track to avalanche conditions that killed workers at rates railways couldn't sustain. Between 1885 and 1916, over 200 workers died in avalanches along the Rogers Pass route. The railway built 6.4 kilometers of timber snowsheds to protect trains and crews. The snowsheds helped. They weren't enough. The catastrophic event came March 4, 1910. An avalanche near Rogers Pass buried 62 workers despite nearby snowsheds. The death toll exceeded any previous railway disaster in Canadian history. Canadian Pacific began planning alternatives. The pass couldn't be abandoned. It was the only practical route through the Selkirks. But surface operation was becoming untenable both financially and morally. Operational costs compounded the problem. Maintaining snowsheds consumed resources. Clearing slides disrupted schedules. The 2.2% grades required pusher locomotives. Additional engines coupled mid-train to assist with climbing. Trains exceeding 1,016 tons had to be cut into smaller sections. Grand Trunk Pacific Railway, using Yellowhead Pass to the north, could haul 2,041 tons with a single locomotive over gentler grades. Canadian Pacific was losing competitive advantage because of terrain. The solution was clear by 1912. Tunnel beneath the mountain, eliminate the surface grades, bypass the avalanche zones entirely. Construction began April 2, 1914. Contractors. Foley Brothers, Welch and Stewart approached from both portals simultaneously. The tunnel would measure 5.022 miles from portal to portal, passing 110 meters below the mountain peak. At completion, it would be the longest railway tunnel in North America. The geology was favorable. All crews encountered predominantly granite bedrock, stable, load-bearing rock that required minimal support during excavation. Some sections showed crumbly slate, necessitating timber supports during the bore, but the majority of the tunnel passed through solid granite. The mountain wasn't going anywhere. Unstructural collapse wasn't a credible risk. The original plan called for timber supports at the portals and sections where rock quality was marginal. The center sections, where granite was strongest, would remain unlined. This was standard practice for rock tunnels in stable geology. Expose the bedrock. Confirm stability, leave it bare. The rock carries the load. No liner needed. But Canadian Pacific engineers specified concrete lining for the portal sections anyway. 7,800 feet total. The justification: protection against long-term water infiltration and surface weathering at the entries where rock was exposed to weather cycles. The tunneling proceeded. Pioneer headings from east and west met in December 1915. The main bores connected in July 1916. The concrete work at the portals was underway. The tunnel opened for revenue service December 9, 1916, 11 months ahead of schedule. Prince Arthur, Duke of Connaught, officiated the opening ceremony in July. The railway renamed the tunnel in his honor. Trains began bypassing Rogers Pass immediately. The route was shortened by 4.3 miles, and the grades were reduced. Pusher locomotives were no longer required for most freight. The tunnel was a success. Then came the decision that defines the structure's longevity. Between 1916 and 1920, Canadian Pacific observed the tunnel's performance. Water infiltration occurred in sections where rock was exposed, not catastrophic seepage, but persistent dampness. Winter freeze-thaw cycles in unlined sections showed minor surface spalling where moisture penetrated cracks. Nothing structural, nothing urgent. But the railway's engineers recognized a long-term concern. And in December 1920, Canadian Pacific awarded a contract to Sidney E. Junkins Company for comprehensive concrete relining. The scope? Remove timber supports, pour reinforced concrete lining throughout the entire 5.022-mile length, not just the portals. The contract specified 50,000 barrels of cement. And the cost? $1.5 million initially, ultimately reaching $2.6 million by completion in 1925. This was in addition to the $6.04 million tunneling cost. The railway was spending an additional 43% on lining a tunnel through stable rock. The work proceeded in sections. Its concrete was mixed on-site and poured against forms erected inside the tunnel. The thickness varied by location, approximately 2 feet at the crown and walls, thinner at the invert where the track rests. Steel reinforcement was placed to handle thermal stress and shrinkage cracking. The concrete wasn't there to hold up the mountain, but the granite was doing that. The concrete was insurance against water, against freeze-thaw, against deterioration modes that might emerge over decades. Modern analysis shows the precaution was excessive for the immediate threat. Granite tunnels in similar geology operate for decades with partial lining or no lining at all. The Moffat Tunnel in Colorado, completed 1928, uses concrete lining selectively, only in sections where rock quality demands it. Substantial lengths remain unlined. The Cascade Tunnel in Washington, opened 1929, employed similar selective lining based on rock conditions. And both tunnels function today without the comprehensive coverage Connaught received. But Canadian Pacific wasn't designing for immediate conditions. The railway was designing for maximum credible deterioration over a lifespan that might extend beyond the era of steam locomotives, beyond the careers of anyone making the decision. And the engineers in 1920 had no way to predict how long the tunnel would be needed. They designed for the worst case: continuous water infiltration, repeated freeze-thaw cycles, a century of thermal stress from steam locomotive exhaust, and diesel fumes. The worst case didn't materialize. Water infiltration remains minor. Are drainage systems installed during the relining handle? What seepage occurs? Freeze-thaw damage is negligible. The 2-foot concrete thickness provides enough thermal mass to moderate temperature swings. The concrete itself has aged well. Surface carbonation has slightly increased compressive strength over time. The reinforcement shows minimal corrosion where concrete cover remains intact. Inspections in 1954, 1975, and 2015 documented the liner's condition. No structural defects, no load-bearing failures. Surface repairs have been required. Patching spalled sections, sealing cracks, maintaining drainage channels, but the core structure, the 2 feet of reinforced concrete poured between 1921 and 1925, remains functionally unchanged. The tunnel operates today on infrastructure that's 99 years old in a role that's remained constant, moving freight through the Selkirks. Compare this to the Panama Canal locks, completed 1914, roughly contemporary with Connaught. Those locks used concrete walls 8 to 10 feet thick under hydraulic loads. By the 2000s, deterioration required comprehensive retrofit. The canal expansion project, 2007 to 2016, and spent $5.25 billion partly to replace concrete that couldn't handle continued service. Connaught's thinner walls, carrying no hydraulic load, only the weight of passing trains and occasional maintenance vehicles, have required minimal intervention. The overbuilding becomes clear when maintenance costs are examined. Canadian Pacific, and later Canadian Pacific Kansas City, allocates approximately $400,000 annually for Connaught Tunnel maintenance. Most of that addresses mechanical systems, ventilation, lighting, drainage pumps, track. Concrete repairs consume roughly $50,000 to $75,000 per year. Surface work is, while not structural reinforcement, for a tunnel carrying dozens of trains weekly, hauling grain, potash, coal, containers, the maintenance burden is minimal. The tunnel's role changed in 1988 when Canadian Pacific opened the Mount Macdonald Tunnel, and a parallel bore 14.66 kilometers long, running 90 meters lower than Connaught, with gentler grades. Westbound traffic, heavily loaded trains climbing toward the Pacific, shifted to the new tunnel. Connaught now handles primarily eastbound traffic, lighter loads descending from the Continental Divide. It's the reduced service actually extends the liner's projected lifespan. Engineers estimate the 1921 to 1925 concrete could function another 50 to 100 years under current loading. That projection assumes no catastrophic events, earthquakes, major floods, rock falls that breach the liner. But those are the same assumptions made in 1920. The difference is the margin. Modern tunnel lining design would optimize thickness for expected loads with defined safety factors, typically 1.5 to 2.0. The Connaught liner appears to have been designed with factors approaching 3.0 or higher, not because calculations demanded it, but because uncertainty was larger and material cost was secondary to long-term reliability. This wasn't incompetence. It was conservatism born from watching structures fail. Canadian Pacific had experience with tunnels. The company had built and maintained dozens of shorter bores through the Rockies and Selkirks, and they'd observed water damage, freeze-thaw deterioration, maintenance costs escalating as structures aged. The Connaught Tunnel represented a massive capital investment in a critical route. Spending an additional $2.6 million in the early 1920s to avoid potentially much larger retrofit costs in the 1950s or 1960s was rational risk management. The railway also faced competitive pressure. Grand Trunk Pacific had proven that superior routing could win traffic. If Connaught's tunnel required extended closures for major repairs in the 1940s or 1950s, shippers might permanently divert to competing lines. The comprehensive lining was infrastructure insurance, ensuring the tunnel could operate continuously regardless of conditions encountered over decades. The human element appears in construction records. Workers in the relining project worked in shifts, mixing concrete, placing forms, stripping forms, and advancing section by section through 5 miles of tunnel. Ventilation was poor. Steam locomotive exhaust had to be cleared before crews could enter. In 1919, an incident during lining work killed a tunnel watchman when gasoline and kerosene used by concrete mixers ignited. He rushed to alert the portal station, but didn't survive. The work was dangerous. The concrete poured at personal cost. The tunnel endures as monument to that work and to the design philosophy that specified it. The mountain didn't need the concrete. The granite was stable. But the engineers couldn't predict how water would behave over 50 years. On 75 years, 100 years, they couldn't know how freeze-thaw cycles would accumulate. They couldn't foresee diesel locomotives, increased tonnages, temperature extremes from modern climate variability. So they overbuilt. They poured 2 feet of reinforced concrete through 5 miles of mountain that wasn't collapsing. 99 years later, the concrete remains. Trains pass through daily. The liner shows age, surface wear, minor cracking, abstaining from water that does seep, but no structural compromise. Maintenance crews patch and seal, work that takes days, not months. The tunnel doesn't close for major reconstruction. It operates. If the Connaught Tunnel were designed today, specifications would differ. Modern engineering would conduct detailed geotechnical surveys, model water flow, calculate minimum liner thickness for defined service life, optimize material use. The result might be adequate. It might last 50 years, 75 years, require retrofit at predictable intervals. But it wouldn't be 2 feet of reinforced concrete through stable granite. It wouldn't be designed for uncertainty. It would be designed for what we think we know. The difference is visible in what still stands. The Connaught Tunnel, lined between 1921 and 1925, operational for 99 years, requiring minimal intervention. Built not for what was needed, but for what might be needed. The mountain wasn't collapsing. The engineers poured the concrete anyway. The concrete remains.